Good morning to all of you. We continue with our discussion on electrostatics. So, today we will start a very important topic in electrostatics, that is electrostatic potential energy. You have all learnt about gravitational field, and when you have an object in the gravitational field, to move the object you need to exert an extra force. So, imagine we have the ground surface here and I need to move an object from a certain height to another height. So, there is a gravitational force which is trying to pull the object below, and I need to apply a force against the gravitational field to move the object up. And so, I have to do work to move the object from a certain height to a larger height, which means that a work which I am doing actually gets stored in the form of a potential energy of the object. So, the potential energy, I can define a potential energy, which means that the object has some energy here. I move the object from one height to another height, I am moving the object against the gravitational field and I am doing work on the object. And so, when the external force does work on the system, the energy of the system increases, and so the potential energy of the object increases here. So, this is an example in gravitational field which you must have studied earlier on. In fact, if I leave the object here, the object falls down on its own accord, the field pulls the object down and the potential energy of the object gets converted to kinetic energy. We have a similar situation in electrostatics, where we can define an electrostatic potential energy. So, suppose let me assume that there is an electric field pointing down, uniform electric field pointing downwards. Let me call this as the x axis, this is some axis which I call z axis. So, I have a uniform electric field pointing downwards. So, if I have a charge here, say let me take a charge q. So, the charge q will be acted upon by an electrostatic force. Depending on the sign of the charge, the electrostatic force is either downwards or upwards. So, to move the charge from this point to another point, I have to apply an external force, and in that process the external force does work on the system. So, let me assume that I have an object at this point. So, let me call this position as xi and this position as xf. I stands for initial, f stands for final. So, my electric field is pointing downwards. So, as you can see from here, electric field is some constant times I cap with a minus sign. The electric field is pointing in the minus x direction is pointing upwards. So, what is the force, electrostatic force on the charge? It is minus q E naught I cap. That is electrostatic force. To move the object, to move the charge from xi to xf, I need to apply an external force which is negative of this, which is minus f electric, which is equal to q E naught I cap. So, I have to apply a force in the upward direction here to move the charge. So, that is the force that I have to apply externally, and what is the distance I must move? The distance I must move is so let me call this L vector is xf minus xi into I cap. So, I start from xi and move to xf, and I am moving like this from here to here. So, the length which I am moving, the distance by which I am moving is xf minus xi into I cap. So, the work done by the external force on the charge is equal to F external dot L, which is equal to q E naught into xf minus xi. So, if I call this height h, this is equal to q E naught h. So, this is the work done by the external force to move the charge from xi to xf, and this work gets stored in the form of potential energy of the charge. Please note that this is the work done by the external force on the charge. So, this equation is true for all kinds of charges. So, let me try to draw a figure here which sees what happens with various charges. So, I have the electric field pointing down. So, suppose my charge was positive and I move from here to here. So, the work done is equal to q E naught h, and q is positive. So, W is greater than 0. That means, I need to do work on this charge in taking it from this point to this point xi to xf. So, if I call the initial energy of the charge as ui, and final energy as uf, you see here in this case uf is greater than ui. The potential energy at this point is more than the potential energy at this point. So, I have to do work on the charge in taking the positive charge from here to here. Now, what will happen if the charge was negative? So, if the charge was minus q, again xi to xf. Now, in this case the work done is equal to q E naught h is less than 0, because q is negative, here. So, if the initial energy is again ui and final energy is uf, in this case uf is less than ui. So, I am moving like this. So, in moving a positive charge from xi to xf, I have increased the potential energy of the charge. In moving the charge from xi to xf with a negative charge, the potential energy has got decreased. What is happening? What is the difference between these two cases? In this case, the positive charge, there was an electrostatic force on the positive charge which was downwards, and I am moving the charge against the electrostatic force. Here, for the negative charge, the electric field is pointing down and I am trying to move up. The force on the negative charge is upwards, and so my movement is along the direction of the electrostatic force, and in which case actually the field does work on the charge, and so the charge comes out to be negative, the work done comes out to be negative, which means that the final energy of the charge is less than the initial energy. So, you can do similar plots. For example, if the electric field was pointing downwards and my charge was going from here to here, this is xi, this is xf. If this is a positive charge, then I am moving in the direction of electric field. So, you can show that uf is less than ui. In the other case where E is like this, and if I have a negative charge and going from xi to xf, if I am moving like this, the electrostatic force on the charge is upwards and I am moving against. So, uf is greater than ui here. So, depending on the direction of the electrostatic force, if I have to move the charge against the electrostatic force, the work done by the external agent on the charge is positive, and so the potential energy increases. If the movement is along the direction of the charge of the electrostatic force, the work done is negative and the potential energy decreases. This is also consistent with gravitational situation, where if I have to move against the gravitational field, the potential energy increases. If I move along the direction of the gravitational force, the potential energy decreases. The difference between gravitational and electrostatics is, in gravitation there is only one force of attraction, there is no force of repulsion, while in the case of electrostatics you can have either attraction or repulsive forces, and so you can have combinations of positive and negative charges moving against the electric field or along the direction of the electric field. So, I leave it as an exercise to you to draw similar figures for E pointing upwards. So, you may practice, electric field is pointing upwards, you find out what are the initial and final energies, whether they increase or decrease depending on the charge, plus q or minus q, and whether you are moving upwards or downwards. So, I leave this as a small exercise to you, and that will help you to understand whether the potential energy increases or decreases in the various situations. Now, in the example which I looked at, I just took the charge vertically up from one point to another point. Now, it may so happen that my movement may not be vertical. So, let me consider the following problem. This is my x, this is z axis. So, electric field is again pointing downwards, uniform electric field everywhere. So, my objective is to move from one point to another point here. So, let me call the coordinates of this point x I z I, and this is x f z f. So, I start from x I z I and I have to move to this point. So, let me call this A and let me call this B. So, I have to move a charge, let me take a positive charge, I have to move a charge plus q from A to B. Now, obviously, I can have different paths to take the charge from A to B. I can move, for example, first horizontally and then go vertically. Let me call this path 1. I can go vertically first and then go horizontally. Let me call this path 2, or I can go straight like this, path 3. So, I can either take the charge first horizontally here and then take it up, or I can take it first up to the same height and then horizontal, or I can take it at an angle from A to B straight. So, let us try to calculate what is the work done in moving the charge from A to B along these three paths. So, let me look at path 1 now. So, path 1, so let me call this C and let me call this D. So, path 1, first I go from A to C and then from C to D. So, in going from A to C, let me calculate the work done. So, the electric field as before is minus E naught I cap. L vector which I am moving from A to C is equal to Z f minus Z I into k cap. Remember that C, the coordinates of C are actually x I Z f. So, I have not changed the x coordinate, I have only changed the z coordinate, and so this vector connecting A to C is nothing but Z f minus Z I into k cap. So, the work done in moving charge from A to C is equal to so F external dot dl dot L, and F external is minus F electrostatics dot L vector, which is equal to plus E naught I cap into q, the charge which I am having. So, the force is q times electric field dot Z f minus Z I into k cap, which is equal to 0, because I dot k is equal to 0. So, I am actually moving from A to C, I do not have to do any work, which becomes a little obvious because now the electrostatic force is vertical and I am moving horizontally. So, the displacement is perpendicular to the electric field. So, the displacement is perpendicular to the force that I am applying, that I have to apply, and so I do not have to do any work in taking the charge from A to C. Now, from C to B I have to calculate the work done, and this we have already done before. Calculating the work done to move vertically, we have just calculated, and that happens to be, so work done is equal to q E naught into x f minus x I. So, the total work done in moving from A to B via C, that means A to C and C to B, total work done is actually equal to q E naught x f minus x I. Now, let me try to calculate for this other path, path 2, which is going from A to D and then from D to B. So, first is A to D. So, A to D is essentially going from this point vertically up. So, the z coordinate of these two are equal, x coordinate has changed. So, just like before what we did, the charge is taken vertically up. So, from going from A to D, the work done is equal to q E naught into x f minus x I. In going from D to B, just like in going from A to C, I have to move perpendicular to the electrostatic field, and so no work is being done. So, D to B work done is equal to 0. So, total work done by the external force in moving from A to B via D is equal to q E naught x f minus x I, which is the same as the work done in moving the charge from A to B via C. These two work dones are equal. So, now let me calculate what is the work done in going from A to B along path 3. The path 3 is now not straight, it is at an angle. So, path 3. So, path 3 I have essentially I am moving along an oblique direction from A to B. So, let me calculate this vector L vector. So, for path 3 L vector is equal to x f minus x I into I cap plus z f minus z I into k cap. Look at this point. This point has coordinates x I z I, this point has coordinates x f z f. So, this vector joining x I z I to x f z f is x f minus x I I cap plus z f minus z I k cap, and the external force again is equal to minus of a electric force, which is equal to q E naught I cap. So, work done is equal to F external dot L, which is equal to q E naught I cap dot x f minus x I cap plus z f minus z I k cap, which is nothing but q E naught x f minus x I, because I cap dot k cap is equal to 0, which is the same as the work done in taking the charge from A to B via C. So, what we have seen for the electrostatic case is the work done in going from A to B is the same whether I go from A to B via C or via D or straight from A to B. In fact, you can take any arbitrary path connecting A and B, and you will find that the work done in moving from A to B is exactly the same as before, q E naught x f minus x I. So, what this shows us is that the work done is independent of path followed. That is a very important concept. These such forces are called conservative forces. Gravitational force is also a conservative force. The work done in moving a mass from one position to another position is independent of the path taken, and it is an example of conservative force. So, if you have to take a charge from one initial point to another final point, it does not matter what is the path you follow. Let me take as another example because in this case what we had taken was an electrostatic force which was uniform. Now, let me take a case in which the electrostatic field is not uniform, and that is a point charge. So, let me take a point charge q. So, here is my charge. So, I want to move from an initial point, this distance r I, to a final position r f. Okay, that is my. So, I want to move from a charge from here to here. So, let me assume the charge is small q. So, I want to move a charge along the radial direction from point r I to a distance r f. So, let me call this A and let me call this B. So, I want to move a point charge with magnitude q from a point A to a point B. So, again, so what is the electrostatic force? Is q times E, which is equal to q by 4 pi epsilon 0 r square into r cap. That is the electrostatic force on the charge. So, my external force which I have to apply is minus of electrostatic force, which is equal to minus q by 4 pi epsilon 0 r square r cap. And my vector which I am moving is along the radial direction. So, you know that the work done, if the force is non-uniform, integral f external dot dl from the initial point r I to r f. From the initial point to the final point, the dot product of force external force that I am applying dot dl vector. And in this case, as you can see, dl vector is nothing but dr vector, which is actually equal to r dr, r cap dr, because the vector is along the r cap direction. This is the r cap direction, remember we had discussed in Coulomb's law, that is r cap direction. So, the work done now becomes by external force is equal to integral f external dot dl from r I to r f, which is actually equal to, now this is the force is minus q by 4 pi epsilon 0 r square r cap dot dr r cap from r I to r f, which is equal to minus q by 4 pi epsilon 0 integral r I to r f dr by r square, which is equal to minus q by 4 pi epsilon 0 integral of 1 by r square is minus 1 by r I to r f, which is nothing but q by 4 pi epsilon 0 into 1 by r f minus 1 by r I. So, this minus signs cancel off and I get q by 4 pi epsilon 0 into 1 by r f minus 1 by r I. That is the work done by the external force in moving the charge small q from this point A to point B, where r I is the initial distance and r f is the final distance. Now, this equation is valid irrespective of the sign of the charges. So, you can see that, for example, if the charges were both positive, say the charge capital Q is positive and the charge which I am moving is also positive and I move from here to here. So, this is A and this is B. You see, with the positive, the force is repulsive, the force is in this direction, the electrostatic force, and I am moving in the same direction. So, the final potential energy will be less than the initial potential energy. As you can see here, the work done, because work done was equal to q by 4 pi epsilon 0 1 by r f minus 1 by r I. So, here q and q are both positive, r f is greater than r I. So, work done is negative. So, the field is doing work, already the force is repulsive and I am moving along the direction of the force, and so actually the field does work on the system and I have to do negative work. Similarly, you can calculate, suppose I had a plus q here and I had a minus q charge here in going from A to B. Now, q times q becomes negative. So, work done is equal to, so this is minus q capital Q by 4 pi epsilon 0 1 by R f minus 1 by R I. This is negative, this is negative sign. So, this is greater than 0. So, U b is greater than U a. Again this is obvious, because this negative charge, the electrostatic force is attractive, and I have to move the charge against the electrostatic force. So, I have to do work on the charge in moving from A to B, in which case that work which I do gets stored as potential energy of the charge. So, you can work out the other combinations here to find out what is the work done by the external agent in moving the charge from an initial point to final point. You can take different cases where R I is less than R f, R f is more than R I, etc., and I leave the discussion to you. Now, just like in the earlier case, what we will find is, so let me take for example this the charge plus for example q, and I want to move from this point to another point here. So, in the earlier example which we started discussing, the two lines, the two initial and final points were along the same radial line. Now, I am taking 2 points which are not along the same radial line, A, B like this. So, I have to move like this now, I want to move from A to B. So, I can do different kind of combinations. For example, first I can move like this along a circular arc around Q, and then move from here to here. I can move from here to here and then move along the circular arc, or I can have any combination of position paths. For example, I can do like this, I can move along radial, then go like this, then move along radial, then go like this, then move along radial, go like this. Now, for example, if you look at this path, around this path which is a circular arc, the movement of this path is exactly perpendicular to the electrostatic force at every point. At this point, electrostatic force is, if this is a positive charge, electrostatic force is like this and I am moving perpendicular. At this point, the electrostatic force is like this and I am moving perpendicular. At this point, the electrostatic force is like this, I am moving perpendicular till I reach this point, and then I move in the same direction as the electrostatic force. So, here I do not do any work, and here I do the work which I have already calculated as q by 4 pi epsilon 0 1 by R f minus 1 by R I. Similarly, if you look at this path, I go from the distance R I to distance R f along the radial direction, and then I move along the circular arc connecting this point to this point. Along this direction I do the same work as this. Along the arc I do no work because I am moving perpendicular to the electrostatic force. Similarly, you can calculate for any path, what you will find is path independence of work done. So, any electrostatic force that you have, the work done to move a charge from one initial point to a final point is independent of the path, and as I mentioned before, this is a characteristic of conservative forces. So, what does this imply for example? So, let me take a following example. So, I have a charge and then I am moving, I want to move between path A to B like this, and I want to come back. So, let me call this C1 and C2. So, I do a circular path. So, I start from A, go to B and come back to A from another path, along another path. So, let me calculate the total work done. So, total work done is F external dot dl, and this, as I mentioned before, this circle on the integral sign means it is a closed path. So, this is equal to A to B along C1 F external dot dl plus B to A along C2 F external dot dl. Now, I know that as we have discussed, integral A to B along C1 F external dot dl is equal to integral A to B along C2, the second curve F external dot dl. which is actually minus of B to A along C2 F external dot dl. So, the work done in going from here to here is the same as the work done in going from here to here along this path. The work done in going from here to here is negative of the work done in going from B to A, that is what this says. So, you see that these two are equal and of opposite sign, which means that I get the following very important expression, that integral f external dot dl is equal to 0. That means, in a closed path, net work done in a closed path is equal to 0, and this is again a characteristic of conservative forces. The net work done in carrying a charge from A to B back to A through any two different paths, any path, is actually 0. So, you may be doing some work in taking A to B along C1, and then the field does an equal amount of work in bringing the force, bringing the charge from B to A along another curve. So, the net work done becomes 0. So, this is again a part of conservative forces, and so what we can do is, with this we can define a potential energy. We can now define a potential energy electrostatic potential energy. So, let me again take a point charge. Remember, we had calculated the so work done by external force is equal to q by 4 pi epsilon 0 1 by R f minus 1 by R a. Okay. So, remember, in gravitational fields we define the potential energy with respect to some reference. So, normally we say the ground has 0 potential energy. So, when I take a object by a certain height, I do work on the object, and so there is a potential energy stored in the object. Similarly, we will define the electrostatic potential energy at any point with respect to a reference potential, which is, so the reference point is usually chosen, at infinity, and this is 0 of potential energy. So, I will assume that if I have a positive capital Q charge here, if the other charge is at infinity, then there is no energy in the system, there is potential energy is 0, and then when I bring the second charge close to this first charge, I will do work on the charge and I will change the potential energy. So, in this equation, if I substitute R I is equal to infinity and R f is equal to R, that means this will give me the work done in bringing a charge from infinity to this point, this is a distance R from here. So, work done in bringing a charge small q from infinity to this point at a distance small r will be given by this equation, which I will define as the potential energy here, which is potential energy is potential energy at a position r between these two pair of charges is q by 4 pi epsilon 0 r. Please remember, because the work done is independent of path followed, no matter how I bring the small charge q from infinity to this point, I will have to do exactly the same amount of work. So, I can define a potential energy which only depends on this point, which is the energy to bring a charge small q from infinity to this point, no matter along which path. So, this becomes the potential energy at this point. So, this is the potential energy of a pair of charges separated by a small distance small r. So, if I have a charge capital Q and a small q separated by distance r, the potential energy So, this is the potential energy of this pair of charges. Please remember that if I had calculated the following, suppose I say I have a charge small q and I bring capital Q charge into this point at a distance r from this small charge, I will get the same potential energy. The energy is stored as a in the entire electrostatic system of charges itself, and it only depends on the separation between these two charges through this equation q by 4 pi epsilon 0 r, and this is the potential energy of this system of charges. Although I have brought in small q from infinity to this point, I could have brought capital Q from infinity to this point, I could have moved both charges from infinity together to bring it to a certain distance small r. Whenever finally they land up with a separation of small r, this pair of charges now has a potential energy which is q by 4 pi epsilon 0 r. So, this is for a pair of charges. I can similarly calculate for more charges. So, for example, suppose my final system has 3 charges. So, I have suppose I have to bring 3 charges q1, q2 and q3. My question is, what is the potential energy of this system of 3 charges? So, I do the following procedure. First, I have nothing here. So, I bring charge q1 and place at this point. Because there is no other charge present, I have to do no work in bringing q1 and placing it here. Once having placed q1 here, I bring q2 from infinity to this point. So, let me call this distance r12. So, what is the potential energy between q1 and q2? So, let me call this u12 is equal to q1 q2 by 4 pi epsilon 0 r12. Product of the two charges divided by 4 pi epsilon 0 into separation between them, that is the potential energy of q1 q2 pair of charges. Now, with these two charges present here, I now bring q3 from infinity and place it at this point. So, let me call this distance as r13 and this distance as r23. Now, you see, when I bring in q3 from infinity, I have to do work against the electric field of both q1 and q2 simultaneously. So, what will happen is the work done by me to bring in charge q2 will be essentially. So, let me calculate charge q3, let me calculate the work done in bringing q3 to this point. So, this will be W will be integral f external dot dl, which is from infinity to this point, infinity to this point. So, let me call this point C, A, B, C. So, this is equal to minus of f electric field dot dl from infinity to C, and f electric field is actually the charge, both the charges now produce electric field at this point as a function of distance, and we know that electrostatic satisfies principle of conservation. So, I have q1 by 4 pi epsilon 0 r square r cap plus q2. Let me write like this. Okay. So, f electrostatic is equal to q1 times E1 electric field because of charge q1, sorry q3. The force on this charge q3 is q3 times E1 plus q3 times E2. E1 is electric field produced by charge q1, E2 is electric field produced by charge q2. This is the force on the charge q3 because of electric field of q1. This is the force on the charge q3 because of electric field produced by q2, and so this is the total electric field that the charge q3 has to move against. So, the work done will be equal to minus q3 times E1 dot dl infinity to C minus q3 infinity to C E2 dot dl. Now, what is this? This is the work done in bringing a charge q3. This is the work done in bringing a charge q3 because of the electric field produced by q1. There is no dependence on q2 here, and that must be, as we have discussed before, q1 q3 by 4 pi epsilon 0 r13, because E1 is the electric field produced by q1 and this is the work done in bringing q3 from infinity to this point at a distance r13 from here. So, the work done is exactly the same as this equation, except that q2 gets replaced by q3 and this distance r12 gets replaced by r13. So, I get a work done which is q1 q3 by 4 pi epsilon 0 r13, and this is nothing but the work done in bringing charge q3 from infinity to this point because of the electric field generated by q2. So, this must be equal to plus q1 q2 q3 by 4 pi epsilon 0 r23. So, this is the work done in bringing q3 to this point. So, the total work done in assembling this charge distribution is the sum of the work done in bringing charge q2 to this point and the work done in bringing charge q3 to this point. So, the total work done or total potential energy is equal to q1 q2 by 4 pi epsilon 0 r12 plus q1 q3 by 4 pi epsilon 0 r13 plus q2 q3 divided by 4 pi epsilon 0 r23. So, this is the energy because of q1 q2, this is the energy because of q1 q3 and this is energy because of q2 q3. That is the total energy of the system of charges, and as I mentioned we associate this potential energy with the entire system of charges. I have now brought, first I brought q1, then I brought q2, then I brought q3. You can calculate and show that this is independent of whether I bring q1 first or q3 first, as long as finally the charge distribution sits in this particular pattern, the work done it will be equal to this, and so the total potential energy stored in the system is the sum of these three. So, it is independent of the sequence of bringing of these charges. So, in general you can write, you can actually generalize this to any number of point charges and you get the total potential energy. So, having looked at potential energy, we now introduce a very important concept in electrostatics again, which is the electrostatic potential. So, electrostatic potential is the work done by an external force in bringing a unit positive charge, work done by an external force in bringing a unit positive charge from infinity to the point is the electrostatic potential at that point. So, it is essentially the work done in bringing a unit positive charge from infinity to that point. So, remember we had discussed, if I had a charge capital Q and if I have a if I bring a small charge q here at a distance r from here, the potential energy was u was capital Q small q by 4 pi epsilon 0 into 1 by r f minus 1 by r I. So, this is the potential energy at this point, or change in energy in bringing a charge from r I to r f. So, the potential energy was when I put r I is equal to infinity. So, potential energy u becomes q q by 4 pi epsilon 0 r at this point. So, if I take a small charge capital Q as unit charge, then I will define the potential at the point r as V of r is equal to Q by 4 pi epsilon 0 r. This is for a point charge. The potential of a point charge is essentially given by Q by 4 pi epsilon 0 r. So, if you have a positive charge here, as you move along this direction, r increases and the potential keeps on decreasing. So, this is decreasing like this. For a negative charge, the potential will be, if I move along the same direction, for a negative charge, the potential will be increasing. So, depends on the sign of the charges whether the potential increases or decreases as you move away from the charge. So, this is the potential at any point is defined for, this is the potential for a point charge. So, for any general electric field distribution, you can define an electrostatic potential as the work done in bringing a unit positive charge from infinity to that point. So, if you have to, for example, if I had a positive, if I have a point charge q, so if this point is say r I and another point is r f, what is the work done in bringing in taking a charge from r I to r f? So, work done by the external force will be equal to the potential at r f minus potential at r I for to take a unit charge, unit positive charge. So, difference in potential gives me actually the work done in taking a unit positive charge from one point to another point. So, potential is a very important concept in electrostatics, and as you can see here, the electric field decreased as 1 by r square, the potential decreases as 1 by r, and there is a unit which is used for potential, unit of potential is volt. This is after an Italian scientist, Alessandro Volta, who was who worked during the years 1745 to 1827. He was a great scientist who did a lot of work in electrostatics, and this name is this potential unit potential is named after him. So, you can also then find another unit for electric field, because as you can see here, potential is q by 4 pi epsilon 0 r, the electric field of the charge would have been q by 4 pi epsilon 0 r square. So, you define an electric field as volt per meter. This is the SI unit of electric field, volt per meter. We have seen earlier other units for electric field. This is another standard unit which is used for electric field. Now, let me do an example to calculate some numerical values of potential. So, here is an example. So, I have plus 10 nanocoulomb, I have another charge here minus 10 nanocoulomb separated by distance 6 centimeters. In the equatorial plane, I consider a point here, this is 4 centimeter, let me call this point A. I consider another point here B, this is at a distance of 4 centimeter from here, and a third point C, which is at at a distance of 4 centimeter from here. Okay. So, I have plus 10 nanocoulomb, minus 10 nanocoulomb, and these two charges generate an electric field. I want to calculate the potential at different points. So, first let me start calculating potential calculation. So, V at A. Now, potentials also satisfy principle of superposition. So, the potential at A, total potential at A is the potential at A because of plus 10 nanocoulomb plus the potential at A because of minus 10 nanocoulomb. So, if what is this distance? If this is r, because I am taking A on the equatorial plane, this distance is also r. So, potential at A is so let me call this q1 and q2, q1 by 4 pi epsilon 0 r. So, plus q2 by 4 pi epsilon 0 r. The distances are equal and q2 is equal to minus q1. So, this is equal to 0. So, the potential at this point is 0, because that is in the equatorial plane. This produces a positive potential here, that produces a negative potential here, and so the total potential at this point A is 0. Let me try to calculate the potential at the point B. So, V at B, q1 by 4 pi epsilon 0. So, this I must calculate these distances now. So, let me call this r1 and the other distance r2, r1 minus q2 is minus q1. So, 4 pi epsilon 0 r2. So, let me substitute these numbers. So, V at B is 10 nanocoulomb, 1 by 4 pi epsilon 0 is 9 10 to the power 9 divided by r1, r1 is 4 centimeters. So, 4 into 10 to the minus 2 minus 10 nanocoulomb, 4 pi epsilon 0 term here divided by r2, which is 4 plus 6 10 centimeters. Please be careful with units, I am using SI units everywhere. So, this comes out to be 2.25 into 10 to the power 3 minus 9 into 10 to the power 2, which is equal to 1.35 into 10 to the power 3 volts. So, that is the potential at this point. So, that is the work done in bringing a unit charge, positive charge from infinity to this point, and that is equal to 1.35 10 to the power 3 volts. You can similarly calculate the potential at the point C. So, V at C will be equal to, so I leave this exercise to you, this is minus 1.25 into 10 to the power 3 volts. Please note this point is closer to the negative charge here than the positive charge. So, the total overall potential happens to be 0 minus 1.25 10 to the power 3 volts, and the potential at A was equal to 0. Now, let me leave a problem to you. Problem: calculate the work done in moving a charge of 5 nanocoulombs from A to B and from A to C. So, I leave this exercise to you. Please calculate what is the work done in moving a charge of 5 nanocoulomb from A to B and from A to C. I leave the paths to you choose appropriate paths to calculate the potential the work done. So, it is an interesting exercise for you to understand calculation of forces and the potential differences. Okay. Now, what I would like to do is to look at the potential of a, as another example, potential of a charged conducting sphere. So, I have a sphere of radius r and I have thrown in some charge capital Q. Remember, we have discussed that the entire charge will sit on the surface. So, I will end my lecture here. In the next class, what we will do is calculate the potential due to a conducting sphere which has been put excess charge, and we will get some interesting results from here. Thank you.